So thermodynamics is the study of energy and its interconversion. So thermo referring to energy and dynamics, the conversion from one form to another. So the first law of thermodynamics is that law of conservation of energy. So energy is neither created nor destroyed. You can also express that as the total amount of energy in the universe is constant. Or we often express it as there is no free lunch. So the school my children used to attend had free lunch for all the students because of the income level. So were those lunches free? No. We understand that, right? Someone's paying for them. The government's paying for them. And you're paying taxes to the government, so we're all paying for the free lunches, right? There's no such thing as a free lunch. And what we mean when we refer to this in terms of thermodynamics is you can never design something that's just going to produce energy out of nowhere. They used to have, snake oil salesmen and people selling all these gadgets and stuff, and people would come up with these perpetual motion machines. They're like, this thing just moves all by itself. It's not using any energy source. We could use this to power this, that, or the other thing. All of those things were frauds. Sometimes they weren't intentionally fraudulent, but there was always some energy source that could be found to explain the movement of that object. You cannot create energy out of nothing. You can't get something for nothing. Any questions? It's not a very optimistic law, but it is what it is. So conservation of energy requires that the sum of the energy changes in a system and the surroundings must be zero. So again, we have these gauges. We were transferring energy from the system to the surroundings. Now the system is lower in energy, the surroundings are greater in energy. The total energy of the system is the same. If I gave each of you a $1 bill, I would have lost, $15, $18, and you each would have gained $1. But if we looked at this room as the system and the surroundings together, was any money lost or gained? No, it just got moved around. Okay, so that's how it is with energy. So we can, of course, make this into math. Sorry if you don't like math. We can say that the change in energy of the universe is equal to zero. So the change in energy of the universe would be equal to the change in energy of the system plus the change in energy for the surroundings. One is gaining, one's losing. In the me giving each of you $1 example, I'm losing money. It's coming out of my wallet. That's a negative experience for me. You're each gaining $1. That's a positive experience for you. So if we add, let's just say 15. If we add the minus 15 that I experienced and the plus 1 that 15 of you experienced, that would add up to 0, right? One of these is negative, one of these is positive. This little triangle here is the Greek letter delta, capital delta, and we use that to mean the change in. So delta energy is the change in energy, and just by mutual agreement, we've defined that as the final minus the initial. So if I had $20 in my wallet, I don't actually have a wallet, I have a pocket. If I had $20 in my pocket and I gave each of you $1, then at the end I'd have $5. So for me, the change would be 5, the final, minus the initial, 20, and that would be negative 15. For you, maybe you had $5 in your pocket and I gave you 1. So your final is 6, your initial is 5, and the change is plus 1, right? So energy change can be positive or negative, and just like with your wallet or your pocket, your bank account, coming in is positive, leaving is negative. We also have something called internal energy. So this would be the energy of a specific object, and that would be adding up the kinetic energy, the potential energy of all the particles that compose that object or that system. Now, that's not something that we can really measure. So that's why we end up looking at changes. When we look at the change in the internal energy of a system, the change in energy only depends on the beginning and the end. Just like the change in my financial situation only depends on the final state and the initial state. That's the same whether I burned those 15 $1 bills, or I gave them all to one person, or I gave one to each of you. Doesn't matter how the change occurred, the change is the same. It's a state function. It only depends on the initial and final. The process doesn't matter. And that's important because it simplifies a lot of these calculations. So we can say that the change in energy is the final energy minus the initial energy. So for internal energy of a system, that's very difficult to measure, but the change in energy is easier to measure. So we can look at the change in energy for a chemical reaction. And that's the final energy minus the initial energy, the energy of the products minus the energy of the reactants. So let's talk more about what a state function is. State function is something that only depends on the initial and the final points. It doesn't matter how you got there. So here we have an example of climbing a mountain. There are two paths. You can take path A, which snakes its way up the mountain, and it's actually 12 miles of hiking. Or you can take path B, which goes straight up the side, and that's a distance of 5 miles. If you start at the bottom and you go to the summit up here, your change in elevation is 10,000 feet. Because up here, you're 10,000 feet above sea level, you started out at sea level, the change in elevation is 10,000 feet. Does it matter which path you took? Doesn't. Change in elevation is a state function, doesn't matter how you got there. You could also get in a helicopter and get flown over here and drop down. We'll call that path C. That's what I would choose. And so you've traveled up and back down. You've traveled more than 5 miles, probably less than 12. But your change in elevation is exactly the same. Does that make sense? The distance traveled is not a state function, right? Which path you take determines how far you went, but change in elevation, just final and initial. So when we look at changes in energy, it's like this change in elevation. How it got there doesn't matter. Any questions about that? Energy is not something that we can see. I don't know about you, but I'm a very visual person, and I need to be able to see stuff. And if I can't actually see it, I will draw pictures of it or make pictures in my mind so that I can see what's going on. So we use energy diagrams to try to make this more visual. So this is an example of an energy diagram. We generally think of going up on the y-axis as being an increase. So internal energy is increasing as we go up on the page or the screen. And we're going to show our reactants and our products. Here's our reaction that we're talking about, carbon dioxide breaking down into carbon and oxygen. So the carbon dioxide has an internal energy down here. That's the reactant. The carbon and the oxygen products together have higher internal energy than the reactant did. This is not a quantitative diagram, it's just qualitative. We don't know exactly how much the difference is, but we know that this is higher. So when this reaction occurs, we're going from a low energy something to higher energy. If I go from $5 in my wallet to $20, is that positive or negative? It's positive, right? The final minus the initial is a positive number. Here's the initial, here's the final. The final is larger than the initial. So this change in energy is positive. What that means is that energy came from the surroundings into the system. Because if I've got $15 more than I started with, where did that money come from? Had to come from somewhere, right? You can't just create money out of nothing. And we're not talking about counterfeit money. We're talking about just real, regular money. Okay? It's got to come from somewhere. It's going to come from the surroundings if I am the system. It's going to come from somewhere outside of me. So the surroundings are losing energy. The energy is going into the system. So the change in energy for the system is positive. The change in energy for the surroundings is negative. Does that make sense? If we look at the same chemical reaction, but now in the opposite direction, we're taking the carbon and the oxygen and combining them to form carbon dioxide. Well, carbon and oxygen are still the same things. They have higher internal energy than carbon dioxide. Now what we're describing is going from the reactants having higher energy and the product having lower energy. So this change for the system will be negative. What's negative for the system is positive for the surroundings, right? If you are my surroundings and money leaves my wallet, it's positive for you, it's negative for me. Any questions? So if energy leaves the system, it has to flow into the surroundings, all of it. Can't have stuff disappearing. So when energy flows out of a system, the change in energy for the system is negative. Energy flowing into the surroundings, the change in energy for the surroundings is positive. So there's a lot of positive, negative here, and it can be easy to confuse that. So just think about money in your wallet or your pocket and how you feel when money comes into your pocket. I like that. It's positive, right? And what if money leaves my pocket, goes away, somebody takes it? Negative, right? So that's the same with the system. Energy coming in is positive, energy leaving is negative. The surroundings have a different point of view, right? Because if I give $5 to Armias, it's positive for him and negative for me. It's the same number, but our experience is opposite. Does that make sense? So we can say that the change in energy for the surroundings is equal to the change in energy for the system. It's just opposite in sign. And so we can write it that way, or we can write it this way. It means the same thing. Writing it this way does not mean that this is positive and that's negative. It means that the change in this is opposite in sign to the change in that. So if I have a change of -5, and he has a change of +5, my change is equal to negative of his change. We can go from here to here just by multiplying both sides by -1. So we talked about heat and work being how energy is exchanged between system and surroundings. So heat and work are the transfer. We use a lowercase w to represent work and a lowercase q to represent heat. Don't ask me to explain that one, I don't know. Q is heat. Heat and work are not heat and work are not state functions. They're like the distance traveled up the mountain. They do depend on the process. The difference in elevation doesn't depend on the process, but how you got there. That's the heat and the work. The change in energy is equal to the heat plus the work. They could both be positive, they could both be negative, we could have one positive and one negative, but these are, these are going to add up to equal the change in energy. So sign conventions. This is not a big meaning for signs to figure out what they are, is it? It's what we've decided to do with the signs. So Q is heat. If the system gains thermal energy, we say that's positive. So that's heat energy coming in, I'm getting warmer. That's a positive. If the system loses thermal energy, its temperature is going down, heat is leaving, that's considered negative. Okay? Work. Work is positive if it's done on the system, negative if it's done by the system. So let's maybe think about a nice shoulder massage, right? If I'm giving you a shoulder massage, I am doing the work. That's kind of tiring for me. It's not something I really enjoy doing. It's sort of a negative experience. But you having your shoulders massaged, the work is being done on you. That's a positive experience for you. Or someone coming to mow your lawn. They're doing work for you. That's positive for you, negative for the person who's doing the work. Does that make sense? And change in energy, energy coming in is positive, energy leaving the system is negative. So here we have, again, the billiard table. Here we have a ball that has an initial kinetic energy of 5 joules. As it rolls across the table, this is a real table, there is friction, right? And that ball will gradually slow down. It is losing its kinetic energy as it moves across. That energy is not lost to the universe, though. It's not destroyed. It's just being transformed into another form, and that form is heat. So as it moves across, it's losing some of its kinetic energy as heat. So it lost half a joule as it rolled across the table. Then it collides with the other ball. In that collision, it's doing work on the other ball. The other ball goes off with the remaining 4.5 joules of energy. This ball now has 0 kinetic energy. So we can look at the change in energy for that white ball. It lost 4.5 joules as work that it did, and it lost half a joule of heat transfer through friction. So its total change is -5. It started with +5, it ended with 0. The change is 0 minus 5. That make sense? If we look at a rough pool table, this one maybe has been abused, not taken care of. Now as we roll the ball across the table, the friction, the rough surface is going to cause the ball to slow down more quickly, right? So now it's losing 3 joules of heat as it rolls. If you're not familiar with pool tables, think about rolling a tennis ball on the carpet and on a tile floor. On a tile floor, it'll just keep rolling much easier than on carpet. It'll slow down. Same idea. Now when that ball hits the purple one, it only has 2 joules of kinetic energy left to do work on that purple ball. So the heat and the work are different. It's done 2 joules of work. It's lost 3 joules of heat. Its total energy change, though, is the same. It started with 5, it ended with 0. Final minus initial, 0 minus 5. The change in energy is still -5 joules. Okay, so the heat and the work, how it happens matters. The overall change in energy doesn't matter how.
Will it ever be like the heat could be 4 and then the work
No, no. That's an excellent question. Could these numbers be such that maybe we lost 4 joules of energy and then did 2 joules of work? That's not possible. Yeah. Now, it's possible that one of these is positive and one's negative, or there could be something else happening here. I could give the ball a push, and that would be adding in another form of energy, maybe work being done on this ball before it does work on another ball. Yeah. When we observe everyday objects, we don't always, in fact, we usually do not see conservation of energy, because how many of you realize that there was heat being given off when you roll a ball across a surface, right? We can't detect that. We're not taught that in elementary school or anything. We're just not aware of that. So we roll a ball on the grass or on carpet, and we see that it slows down, and we're like, oh, well, you roll something and it slows down. It just loses energy, right? How does that even happen? Well, yeah, it lost energy, but it transferred that energy to the surroundings. So in those examples, the change in energy for the ball is the same, but Q and W are not the same. The sum of Q and W is the same on both tables, even though individually Q and W are different from each other. Delta E for the system, the energy lost by the first ball, is equal to delta E for the surroundings in the opposite direction. That would include the second ball and the table and anything else nearby. So heat is a transfer of thermal energy, and that happens because of a temperature difference. Thermal energy always flows from a warmer object to a colder object. Temperature is the measure of the thermal energy. So heat will flow, heat transfer will occur until the objects are at the same temperature. Once the objects come to the same temperature, we call that thermal equilibrium, then there's no additional net transfer of heat. So let's look at this example. The cylinder and piston assembly, defined as the system, is warmed by an external flame. The contents of the cylinder expand, doing work on the surroundings by pushing the piston outward against the external pressure. If the system absorbs 559 joules of heat and does 488 joules of work during the expansion, what's the value of delta E? So there's a lot of words in there describing some things that you might have a hard time picturing. You don't actually need to understand all of those words. Let's do what we've done before and pull the numbers out and see if we can identify what they are. So there's 2 numbers given here. We've got 559 joules, and we've got 488 joules. 559 joules of heat. What's the symbol for heat? That's Q. You can say Q equals, and 488 joules of work. That's what? W. Now we have to consider the sign on these. It says the system absorbs 559 joules of heat. Is that positive for the system or negative? It's positive. The heat is coming in. So we don't have to put a positive sign here, but I'm going to put a positive sign there just to remind myself I thought about this and I decided it was positive. And it said the system does work. For the system, is that positive or negative? That's negative, because it did work on something else. Okay, any questions? So we're asked to find delta E for this system. The change in energy is equal to the sum of Q and W. So Q is 559 joules, and W is negative 488 joules. Now, when you're adding negative numbers, don't overthink this. You can just let your calculator do the thinking for you. So you can do 559 minus 488, or you can do 559 plus negative 488. We should end up with the same answer, 71 joules. So that's a positive number. So in the process of the system absorbing heat and doing work on its surroundings, overall it had a gain in energy that came from the surroundings. Any questions?